Welcome! Today, we'll be walking through an interesting problem, number 1173, titled Invalid Problem ID. While the problem metadata is missing, this gives us a unique opportunity to explore how to approach ambiguous or incomplete tasks systematically. Let's dive in. LeetCode problem number 1173, titled Invalid Problem ID, does not correspond to any valid or existing problem on the LeetCode platform. This means that there is no specific problem statement, input-output format, or constraints associated with it. Additionally, there are no example test cases available, as the problem ID itself is invalid. If you have encountered this issue while trying to access a problem, it is recommended to verify the problem ID or consult the LeetCode platform for further clarification. When approaching a scenario like Invalid Problem ID, where no specific problem description or requirements are provided, we need to think systematically. The first method we can consider is a brute force approach to simply check for errors. The intuition here is that the issue might stem from user error, such as providing an incorrect problem ID. To address this, we would manually validate the ID by cross-referencing it with a known list of valid LeetCode problems, either directly on the platform or through an API. This ensures that any potential human error is identified and corrected upfront. However, while this approach is straightforward and effective for identifying issues caused by a typo or mistake, it doesn't resolve the situation if the problem ID is inherently invalid. Another option to explore is an optimized fallback handling approach. Here, the intuition is to create a systematic response for invalid problem IDs by detecting them through an API or database query. Once identified, we can return a clear and standardized message, such as invalid problem ID. Please check the input and try again. This approach not only provides users with actionable feedback but also ensures that the system handles such errors gracefully. However, implementing this requires access to up-to-date problem ID data, which could be a limitation in certain scenarios. Building on the fallback handling approach, we could further enhance the user experience by suggesting similar or nearby problem IDs. This would involve leveraging algorithms or database queries to find related IDs, helping users locate the correct one more easily. While this adds an extra layer of functionality, it does come with trade-offs, such as requiring robust access to an API or a database of problems, which might not always be feasible. Alternatively, a more generalized approach to error management could be considered. This involves creating a framework capable of handling not just invalid problem IDs, but a wide range of similar issues. The first step would be to implement a logging system that tracks invalid requests, allowing us to analyze patterns over time. With these insights, we could improve input validation mechanisms and design an adaptive error handling system that evolves based on user behavior. While this approach is highly scalable and forward-looking, it requires substantial investment in infrastructure and development resources. However, its benefits lie in the ability to address not just this specific issue, but a broader category of potential problems, making it a versatile long-term solution. After evaluating the different approaches, the chosen strategy is fallback handling for invalid problem IDs. This approach strikes the right balance between simplicity and enhancing the user experience. The intuition is that most invalid problem ID issues arise from either user error or backend inconsistencies. By implementing fallback handling, we can directly address the problem by providing users with clear guidance, such as a standardized error message. This solution stands out because it automates the validation process, unlike the brute force method, which requires manual effort. Compared to generalized error management, fallback handling remains focused and is easier to implement for this specific scenario. While it does not resolve deeper systemic issues, it effectively addresses the immediate concern and ensures users receive actionable feedback. In conclusion, fallback handling prioritizes clarity and simplicity, creating a solution that is both efficient and scalable. By addressing the immediate needs of users while maintaining ease of implementation, this strategy offers the optimal balance for resolving the invalid problem ID scenario effectively. When working with a problem titled Invalid Problem ID, and limited information is provided, the challenge often centers on dealing with incomplete or erroneous inputs. This is a common scenario in systems that process user queries, interact with databases, or integrate with external APIs. To address this, the algorithm must focus on robustness by validating inputs effectively and ensuring the system can handle errors gracefully while delivering meaningful feedback. The first step is input validation. Here, we check whether any input has been provided at all. If it's missing, the system should return an error message like, "Problem ID is required." Next, we verify if the input follows the correct format. For example, if the problem ID is expected to be an 8-character alphanumeric string, we can use a regular expression, such as $AZAZ0-9, $8, to validate it. If this check fails, the system should respond with feedback like, "Invalid problem ID format." This ensures that only well-formed inputs proceed to the next stage, reducing the likelihood of cascading errors later in the process. Once the input has been validated, the next step is to check if the problem ID exists in the database or the problem repository. This involves querying the database with the given ID. For example, in SQL, a query like select asterisk from problems where ID equals problem_ID can be used. If the query returns no results, the system should respond with a clear message such as, "Problem ID not found." This ensures users are aware that the ID doesn't exist in the system. Beyond validation, it's important to log these invalid inputs and errors for future analysis. Logging should capture details like the invalid ID, a timestamp, and, if available, user information. For instance, a log entry could look like, "Invalid problem ID, ABC123, user 123, timestamp, October 1, 2023 t14 hours and 23 minutes c." Such logs are invaluable for debugging and detecting patterns, such as repeated invalid requests that might indicate abuse. To safeguard against misuse, it's also wise to implement mechanisms like rate limiting to control the frequency of requests. If the problem ID is valid and found in the database, the system should fetch the associated data, such as the problem's title, description, and constraints. Otherwise, invalid or missing IDs should consistently return standardized error responses. Now, there are some key insights to keep in mind to improve the efficiency and reliability of this algorithm. First, input validation is critical. By catching invalid inputs early, we not only ensure data integrity but also save system resources by preventing unnecessary database lookups. Next, for database lookups, it's essential to optimize search efficiency. Indexing that ID column in an SQL database, for instance, ensures that queries run quickly even as the database grows. On the error handling side, structured logging plays a vital role. By logging invalid inputs in a structured format, such as JSON, it becomes easier to parse and analyze this data, whether for debugging or identifying patterns of malicious activity. Another important aspect is user feedback. Providing clear and actionable error messages, such as invalid format versus ID not found, greatly enhances the user experience, as it helps users understand and correct their mistakes. In terms of data structures, using an indexed database table is a great choice for storing problem IDs and their metadata. Alternatively, if the set of problem IDs is relatively small and frequently accessed, loading them into an in-memory hash set can offer O1 lookup time. Finally, structured logs ensure that error-related data is easily accessible for monitoring and system improvements. To make the algorithm comprehensive, it's essential to account for edge cases. For example, the system should handle empty inputs gracefully, ensuring that null or empty strings don't lead to unexpected behavior. Malformed IDs should be caught during input validation to confirm they meet the required format. For non-existent IDs, the system should respond with clear and constructive feedback, guiding users to provide the correct input. Additionally, the database should enforce unique constraints to avoid issues with duplicate IDs. From a complexity standpoint, input validation is efficient, operating at O1, since it typically involves simple length and format checks. Database lookups, when performed on indexed columns, generally operate at O log n, while an in-memory hash set would provide constant-time lookups at O1. Overall, the algorithm's complexity is primarily determined by the lookup step, making it crucial to optimize database search efficiency. By addressing these edge cases and optimizing performance, the solution becomes robust, scalable, and user-friendly. This Python implementation addresses the issue of handling an invalid problem ID. The goal is to validate input problem IDs and handle cases where the input is either invalid or refers to a non-existent problem. The implementation consists of a single method handle_invalid_problem_id within the solution class. This method takes an input problem_id and performs the following. 1. Input validation. The method first checks whether the input is a positive integer. If not, it immediately returns an error message stating that the problem ID is invalid. For example, inputs like -5, 0, or a string would result in error, invalid problem ID. 2. Problem existence check. If the input passes the validation, the method simulates a lookup in a set of existing problem IDs, existing_problem_IDs. In the real world, this could represent a database or API lookup. If the problem ID is not found in the set, the method returns error, problem ID does not exist. 3. Valid and existing ID. If the problem ID is both valid and exists in the set, the method returns a success message indicating that the problem ID is valid and exists. ###example usage. Handle_invalid_problem_ID 1173 checks an ID that does not exist in the set and returns error, problem ID does not exist. Handle_invalid_problem_ID -5 validates a negative input and returns error, invalid problem ID. Handle_invalid_problem_ID 1172 recognizes a valid and existing problem ID and returns problem ID 1172 is valid and exists. This solution is robust, concise, and handles edge cases like non-integer inputs and IDs outside the valid range. It demonstrates how to validate and process erroneous or incomplete data effectively in a system. In this Java implementation, we start by defining a method called handleInvalidProblemID, which takes an integer parameter problem ID. The first step in this function is to check if the provided problem ID is valid, meaning it must be a positive integer. If the value is less than or equal to 0, we immediately return an error message stating error, invalid problem ID. Next, we simulate a database or a problem registry using a hash set that contains a predefined list of valid problem IDs, such as 1001, 1002, 1172, and 1174. Using the contains method, we check if the given problem ID exists within this set. If it does not, we return another error message, error, problem ID does not exist. Finally, if the ID passes both checks, meaning it is positive and exists in the registry, we construct and return a success message indicating that the problem ID is valid and exists. The main method demonstrates an example usage where we call handleInvalidProblemID with the input 1173. Since this ID is not in our registry, the expected output is error, problem ID does not exist. Now, looking further at the main method, we test the handleInvalidProblemID function with additional inputs. For instance, when the method is called with -5, the input fails the first validation check because it is not a positive integer. As a result, the function returns the error message, error, invalid problem ID. Another example is when we pass 1172 as the input. Since this ID is both positive and present in the registry, it passes all checks, and the function returns the message, problem ID 1172 is valid and exists. These examples demonstrate how the function handles a variety of scenarios, ensuring robust validation for the problem IDs it processes. This structured approach allows us to effectively handle invalid inputs and provide clear feedback to the user. In this example, we start with a problem_ID of 1173. The method handle_invalid_problem_ID begins by checking if the input is a valid integer greater than 0. This is done using the condition not isInstance, problem_ID, int, or problem_ID equals 0. Since 1173 is a positive integer, the condition evaluates to false, so the code moves forward. Next, the method performs a lookup to see if the problem_ID exists in the predefined set existing_problem_IDs, which includes 1001, 1002, 1172, and 1174. Since 1173 is not found in this set, the condition problem_ID not in existing_problem_IDs evaluates to true. As a result, the method concludes that the problem ID does not exist and returns the error message, error, problem ID does not exist. The intermediate outputs reflect the problem_ID and the set of existing IDs, while the final output is the error message. Here, we examine a case where the problem_ID is invalid because it is a negative number. The input provided is -5. The method handle_invalid_problem_ID first checks whether the problem_ID is a valid integer greater than 0 using the condition not isInstance, problem_ID, int, or problem_ID equals 0. Since -5 is less than 0, this condition evaluates to true. As a result, the method immediately returns the error message, error, invalid problem ID, without proceeding to any further checks. The intermediate output shows the problem_ID is -5, and the final output is the error message indicating the invalid input. In this final example, the problem_ID provided is 1172, which is both valid and exists in the set of known problem IDs. The method handle_invalid_problem_ID first verifies if the problem_ID is a valid integer greater than 0 using the condition not isInstance, problem_ID, int, or problem_ID equals 0. Since 1172 is a positive integer, this condition evaluates to false, so the code continues. The method then performs a lookup in the set existing _problem_IDs, which includes 1001, 1002, 1172, and 1174. Here, the condition problem_ID not in existing _problem_IDs evaluates to false because 1172 is present in the set. Consequently, the method determines that the problem ID is valid and exists, returning the confirmation message, problem ID 1172 is valid and exists. The intermediate outputs include the problem_ID and the set of existing IDs, while the final output confirms the validity and existence of the problem ID. In this function, we start by analyzing the time complexity of each step. First, the type and range validation, which checks if the input is an instance of the correct type and ensures the value is greater than 0, consists of constant time operations. These checks involve a straightforward comparison and an isInstance call, both of which execute in O1 time. Next, we perform a lookup in a set to verify whether the given problem ID exists in our predefined set of valid IDs. Because the set is implemented using hash-based indexing, lookups in this data structure, on average, are performed in constant time, or O1. Finally, the return statements, regardless of which branch is executed, involve creating and returning a string. String creation and return are also constant time operations, adding another O1 step. Since each individual operation within the function has a time complexity of O1, the overall time complexity for the function is O1. Now let's explore the space complexity of the function. The input variable, problem_ID, is a single integer. Integers in Python have a fixed memory footprint, so this contributes O1 to the space complexity. Next, the predefined set of problem IDs, 1001, 1002, 1172, 1174, contains 4 elements. The memory used by this set is proportional to its size, but since the set is constant in size and does not dynamically grow, the space usage is still O1. Lastly, the return statements produce small strings, and the memory required for these strings is constant regardless of the input size. With no additional data structures being created and the memory usage of the set fixed, the total space complexity of the function is also O1. To understand the efficiency of this approach, let's compare it with a naive solution. A naive implementation might use a list to store valid problem IDs and perform a linear search to check membership. This approach would require O(n) time for each membership check, where n is the number of problem IDs in the list. However, by using a set, we leverage hash-based indexing to achieve O(1) average case membership checks, which is a significant improvement. Now considering the best, average, and worst cases, in the best case, the input problem_ID is invalid, such as a negative number or a non-integer. Here, the function short-circuits after the initial validation, completing in O1 time in O1 space. For the average case, the input problem_ID is valid but does not exist in the database. The function performs a membership check in the set, which is still O1 in time complexity. Finally, in the worst-case scenario, the input problem_ID is valid and does exist in the database. Even in this case, the function operates in constant time, as all steps, including the membership check and return statements, remain O1. Across all cases best, average, and worst, the time complexity stays constant at 0, 1. To mathematically justify this, we note that the use of sets guarantees 0, 1 average case lookup times due to hash-based indexing. Additionally, all other operations, such as type checks and string manipulation, are also constant time. On the space complexity side, the predefined set has a fixed size, and no dynamic memory allocation occurs during the function's execution. Thus, the overall space complexity remains 0, 1. This makes the solution not only efficient but also highly scalable for scenarios with constant-size datasets. When tackling coding problems, there are several common mistakes that can hinder your progress. First, misunderstanding the problem requirements is a frequent issue. It's crucial to take the time to fully comprehend the problem statement, clarify constraints, and identify edge cases before diving into the solution. Rushing into coding often leads to unnecessary errors. Next, relying solely on inefficient brute force solutions can be problematic. While they can help you get started, they are often too slow for larger inputs. Focus on analyzing time complexity and explore more efficient algorithms to avoid timeouts. Another pitfall is ignoring edge cases, such as empty inputs, single-element arrays, or scenarios involving maximum constraints. These often lead to incorrect or incomplete solutions, so make sure to rigorously test for all possibilities. Off-by-one errors are another common challenge, especially in array-based problems or loops. Tracking indices carefully and double-checking bounds will help prevent these issues. Finally, overcomplicating your solution can create unnecessary challenges. Simplicity and readability should always be priorities to make your code easier to debug and maintain. To excel in coding interviews, there are a few key strategies to keep in mind. Pattern recognition is one of the most important skills to develop. Many problems are variations of common patterns, such as sliding window, two-pointer techniques, or divide and conquer. Identifying these patterns early on can help you approach the problem more effectively. Clear communication is another critical aspect. Walk your interviewer through your thought process step by step. Even if your solution isn't perfect, explaining your reasoning can demonstrate strong problem-solving skills. Time management is also essential. Allocate your time wisely by spending the first few minutes understanding the problem, then planning your approach before jumping into coding and testing. Lastly, focus on optimizing iteratively. Start with a basic, brute force solution if needed, and then refine it into a more efficient version. Interviewers appreciate seeing a clear progression of thought and your ability to improve upon your initial approach. To build your problem-solving toolkit further, it's helpful to study related problems. For example, the two-sum problem, which is LeetCode 1, is a classic that demonstrates how hash maps can optimize search operations. Another great example is the longest substring without repeating characters, or LeetCode 3, which highlights the sliding window technique. The container with most water problem, LeetCode 11, is a two-pointer problem that focuses on maximizing values. Additionally, three-sum, or LeetCode 15, combines sorting with two-pointer approaches for efficient solutions. Beyond related problems, it's also important to understand different approaches to solving them. A brute force method, while simple and intuitive, is usually inefficient and best suited for smaller input sizes or clarifying the logic. Optimized algorithms, on the other hand, leverage data structures like hash maps, heaps, or binary search to achieve better time complexity. For instance, moving from O(n) squared to O(n) asterisk log n, or even O(n), can make a significant difference for large datasets. Another powerful approach is divide and conquer, which is particularly useful for recursive solutions, such as merge sort or binary search-based problems. In problem solving, it's important to evaluate trade-offs between different approaches. One common trade-off is space versus time. For instance, using hash maps can significantly improve runtime performance, but this comes at the cost of additional memory usage. If memory constraints are a concern, you may need to consider alternative solutions that use less space, even if they are slightly slower. Another trade-off to consider is readability versus performance. Cleaner and more readable code is easier to debug, maintain, and explain, which can be especially important in interviews. However, in competitive scenarios, you may need to prioritize highly optimized solutions, even if they involve more complex or less readable code. Striking the right balance between these trade-offs depends on the specific problem and the context in which you're solving it. Thanks for watching. Today, we discussed how to systematically approach a problem even when key details are missing. Remember to focus on clarifying assumptions, generating hypotheses, and exploring potential strategies. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!